Okay, so this morning we're going to be talking about spectral deconvolution. And so, like I said, it's mostly, most of the times I've used it has been in visible spectroscopy, although I did use it in my infrared work. It doesn't really matter what spectral range you're in. A friend of mine used it in X-ray photoelectron spectroscopy, so it's useful in all those different areas. And what we're trying to do is we're trying to find the peak center, the peak width, really not that much information in the peak width. Is it not on? How about that? Yeah. All right, very good. We're trying to find, here's an example spectrum. Let me go ahead and zoom in on it so you guys can see it. I'll make it big. Ooh, too big. Okay. Right, so if this is our spectrum, we could come in with a traditional peak picking technique and come in and kind of hover over that and get our peak center of 3022.5 and our peak height of 0.11. Okay, we could write that down, and that's what we do in an undergraduate level, CHEM. And for this peak, since it's more than 50% resolved, that peak maximum is probably going to be accurate. It's going to be right above the center of the peak. There's a lot of noise in this data, though, so it could be off just because of the noise, right? A point that's not the peak maximum might actually be because of noise counted as the peak maximum. Does that make sense? And so think of my hand as the you understand what I mean. I was going to do an analogy, but that wouldn't work with my hand. Okay, but like I said, because this peak is more than 50% resolved, meaning this dip between the adjacent peak goes down more than halfway, then that peak maximum is probably representative of the center. But what about this one? It's on a slope. See, so the slope of this peak is coming down, right? And this peak is on that slope. And that's going to cause that peak shape to rotate a little bit. And because it rotates, we have a maximum it's biased towards the slope. It's biased uphill. Does everybody understand that concept, right? If you take a peak and you plot it on a slope, it moves up the slope. And the peak maximum has shifted from the center of that transition. And that's a problem. And so what we want to do to get an accurate position of this peak, and this may be really essential for your analysis of peak shifts and so on, then you would want to do deconvolution. So convolution is when we take independent Gaussians and we're simulating a spectrum. We have the Gaussian positions, the widths, and the heights, and then we add them up at each wavelength in the spectrum, and that's convolving the stick spectrum with a Gaussian. So we take the stick, we put a Gaussian on it, and then we add up all our peaks. That's convolution. Deconvolution is doing that in reverse. But we do it in reverse by simulating the spectrum and getting it to match. And then the peak positions that we used in matching the simulation are the peak centers of those peaks. We also have a baseline problem here. So this is not 0. This is 0.03 something. And so that's the first job, is let's get rid of the baseline. Okay, let's model this baseline. And so we have, let me shrink our spectrum again so we have this baseline function. So I'm going to set a baseline offset and a baseline slope. And I'm not using this overall y factor, so I'm just going to go ahead and delete that one. So I have an offset and a slope. Offset is obvious. It's just how high the baseline is off the ground, but then the slope is how tilted it is. Okay, so it's just a linear function. So we come down here for our baseline function, and we have, yes?
Let
me make sure. Yes, it's recording, yeah. Okay, so look at my formula here. I'm going to go ahead and increase the size of this. So if I click on that, no, too big. Okay. So you see the color coding. I have mx plus b. So m, this b3, that's the slope, times x, my wave number value, plus the offset. Okay, does that make sense to everybody? It's just a linear function for my baseline, and I'm gonna hit enter on that, and then I'm gonna copy and paste that down. Now I want it to go all the way to the bottom, however long my data is here. And so I'm gonna copy that. This is a technique for doing this. This is column F, so I'm gonna go back over here, control down, back over to column F, control shift up, and paste. Okay. If they were adjacent to each other, I could double click and it would go down, but sometimes you can't do that. And that's pretty good. There's my baseline, it's plotted. Okay. And you can see that if I change this to 0.01, okay. Now I said this is about 0.03, right? But the offset is 0.01, and then the slope gets us up to 0.03 because we're here at 3,000. So this is 3,000 times this 6 times 10 to the minus 6 slope. So it goes up 6 parts per million for every wave number. So by the time we get to 3,000, it's up at, at 0.03. And so you can fiddle around with this offset, 0.02, okay, it's too high, 0.01 was too low, 0.015 gets us close to the middle. If we change this, if we did 5e minus 6, it's still pretty good. Then we need to maybe go 0.016, 0.017. And so you can play around with your baseline value, and that's the first step that you want to do in doing your convolution or deconvolution. Now, we want to probably do the baseline by hand first and get it close. Because if we try to do solver on the baseline right away, it's going to try to match these peaks with our baseline as well. Let me just show you that. So we can fiddle around this, play with it by hand, and it's really tedious. Or we can have Excel do it, okay? Now, baseline by itself, this is not going to work, but I'll show it to you what happens if you try it. Okay. Oh, we can't until we do the residuals, so never mind on that. I'll show you in a minute. Okay, so that's our baseline. Let's go back to 6 times 10 to the minus 6 and 0.015. Okay, so there's our good baseline. It goes right through our data. And so we do our baseline first, and then we start adding in peaks. And so I'm going to go ahead and go to this next tab where I've got the baseline there, and I'm starting to add in the peaks. Now, I want a nice convenient place to enter my data. And so I have these yellow cells where I enter my data, but each individual peak up here is just referring down to that center for peak 1. This one will be the center for peak 2. This one will be the center for peak 3. And then the height for peak 1, the height for peak 2, the height for peak 3. And then this width, I want them all to have the same width because, there's no need to add complication and have individual widths for your peaks, although they could. You could put individual widths for every peak, but I'm just going to have one spectral line width for our purposes. So here's our peak center, peak intensity, the uncertainty or peak width, and let's create a formula for this. So this is the Gaussian function in Excel, norm.dist. I don't know if you can see that very well. You can see it down here if I double click and increase the magnification. So just a second. Uh-oh. Got the spinny circle. This is a great video, by the way. It's time to tell a joke. So an engineer's walking along the road and, oh, never mind. I'll tell that to you in a sec, though. It's a really good joke. Okay, let me zoom in on this. Okay. And I'm just going to show you this function. Now you can see it. So G4, that's the intensity of the peak. Norm.dist, the first value is the center. So it says X. The first value is your X value. It's over here. It's the wave number value. The second number is your mean. So that's the peak center. And then your third number is your standard deviation, which is your peak uncertainty or your width. Okay, so it's in that order: x-axis, the peak center, the peak width, and the peak intensity is out front. It's multiplying this whole Gaussian function by that. Now I'm making an assumption here that's false. I'm saying that the spectral line width of 10 wave numbers is the same as sigma in a Gaussian, and it's not exactly. We can talk about that later. It's close, but it's not exactly the same. Okay. But it's close enough for our purposes today. Okay, so I'm going to zoom back out and just show you the cells that formula refers to. You see it refers up, the blue cell is the intensity, the red cell is the x-axis, the purple cell is the peak center, and the green cell is the peak uncertainty or width, and that's everything we need to plot a Gaussian function. And so I'm just going to double click that corner. Now that I have adjacent cells to the left, I'm going to double click this corner and that'll paste it all the way down. And I have a peak. Well, I need to plot it on there, but I've already done that for this. So there's peak 1. And we can see it's located pretty well, or pretty accurately here, but my peak width is not good. So I'm going to make that 10. I'm going to knock that back to 5. Yeah, that looks a lot better. If I wanted to change its intensity or what have you, I could change it to 0.5. It would go down. You see how it doesn't change its position, but it just goes up and down. 0.6, it goes back up. Let's change its position. 2985, let's go to 2986. And it didn't move much, but 2990. Yeah, so you can move it around however you want. And then we can move it by hand, and then we can have Excel move it for us. Okay, let's go ahead and copy this over. Now notice how I anchored the cells. These dollar signs in here. So this A20, that's our x-axis. I want to anchor that to column A. So when I copy it over, it still refers to column A. If I don't anchor it and I move it over, then it's going to refer to this experimental column and then the simulated column, and it's going to screw things up. So learning how to anchor cells is critical. Then the G3, that's looking straight up. That's anchoring row 3. And the G5, there's a dollar sign in front of the 5. So that anchors row 5. And this G4 anchors row 4. And so if I copy that to the right, it's going to move the column with it, but it's not going to change the row when I copy it down. And so anchoring column only or row only or anchoring both is a really important skill. So I can just take this corner and copy it to the right, and it's going to create peak 2 and peak 3. See, those center, height, and width moved, but the x-axis didn't move because the column was anchored. Okay. Now if I hit enter and I copy this down, okay, notice here the A went down because the row's not anchored, but up here the rows are anchored, and so they didn't move. And so I'm in the second cell. Okay. And then let's go ahead and do peak 3. So I have all 3 of my peaks here. And now I need to create a sum of all 3. So I'm just going to take this simulated column. I'm going to have a sum of all 3 of these plus the baseline. Okay. So that's this next tab. Yeah. And so that's it. But I do have this overall Y scale offset. I don't know why I put that into the simulation. It's set to 1, so it doesn't really, it's not really involved. But anyway, it could just be equal sum F20 to I20. So it's just all 4 of these columns.
And then you have multipliers.
Yeah, this overall Y factor. It just is a scrunch factor. I don't know. I think I was doing that, for normalization, but I'm not sure why. We're not using it today. Okay, so this is the sum with the peak width of 10. and it's plotted on here. Let me go ahead and I can make this big for you guys since we should be comfortable with those individual peak columns. Okay. So there's our spectrum. The orange is the raw data. This is our simulated spectrum. They don't quite match. Okay. What do you think the biggest problem is right now? Yeah, I think the width is the biggest problem. So we'll just go slowly. I'll go 8. No, not good enough. 5. Yeah, that's pretty good. It looks like we have a peak width close to 5 wave numbers. Okay. What about the centers? Well, it looks like this orange one here, peak number 1 or whatever peak that is. Let's see, which one is it actually? I can click on it and I can see that's peak number 3. Okay, so peak 3 is not high enough. So instead of 3021, I need to go to 3022 maybe. Yeah, I put it in the center pretty well. Okay. This one is 2999. Let's try 3000. It's better. Okay. So that looks pretty good. They're not quite high enough, and so maybe I need to come down here and increase their height, maybe 0.7. That looks pretty good. Instead of 0.9, let's go to 1. Okay, that looks pretty good. Instead of 0.8, let's go to 0.9. So you see, I could play around with this and eyeball it, but that's when do you stop? How do you know how good is? So this is a principle that you need to think about and maybe even write some things down on. Okay, how do you compare two data sets? We have a simulated data set and an experimental data set. How do we compare them? What are you doing with your eye? Looking for differences. Yeah. So with your eye, you're looking for differences. You're looking at these gaps here. Well, we can do that mathematically. We can take residuals. Okay. So the residuals are just differences between experiment and simulation. Now, we always take our pardon?
Sorry, I was thinking out loud. If you take a difference, you get just take a deviation.
Yeah, that's right. So this is a deviation, and we're sort of like we would take a mean value and our x value. We would compare it to the mean. We'd take differences. So we're going down that exact same road. Okay, and so I'm going to go ahead and copy that down, and I have all of these residuals. But notice some of them are positive and some of them are negative. So do you remember the formula for standard deviation?
It's the sum of the squares.
Squares of the differences, right? So the differences are in there. It's the x minus the mean. But because some of those are positive, some of those are negative, we want to square them, okay? And then we square them and we add them together. So we sum them up. We sum of the squares of those differences, and then we divide by the number of data points. So we can do that exact same thing in this formula here. So we have the sum of the squared of the differences, okay? And so let me double click on that so you can see it. So SUM-SQ is the sum of the squares of these values. And then you select that column, D20 to D1120. So we're taking 1,100 differences and squaring them, in one formula. And then I went ahead and divided by the count. Now, sometimes in the standard deviation, we say -1, right? N minus 1. But that's only if you have a small data set. We have 1,100 data points. So we're not going to fiddle with any -1. 1,100 versus 1,100 minus 1. It's not that different, okay? And so we're going to have, in the denominator, the count of that is just counting how many cells we have. And so we have the average. It's a mean of the differences squared at this point. So we're going to take the square root to get rid of that square magnitude. And so then we have the square root of the whole thing. And so that's kind of our standard deviation. So this single number tells us how good our fit is. So it looks like we can make it better by moving the middle peak to a higher wave number value. So maybe instead of 3,000, what do y'all want me to do?
3,001.
3,000 and a half. Okay, 3,000.5. Now look at our standard deviation. It's 0.00379. Everybody see that number? I'm going to hit enter and you'll see it. 379, it went down, didn't it?
Yeah.
I don't exactly know why it went down. Oh, we moved it up and we lost some of the fit that we had here. Okay. So maybe it's definitely too low. Maybe we need to move it up. I like the new position. I don't want to go back. But maybe going up would yield a better fit. So let's raise its intensity for peak 2 from 1 to what? What do you want to? You choose. Good. Okay, put 1.001, so tiny change. Okay, we'll try it. 1.001, no problem. All right, let's see what happens to our standard deviation. We're at 0.00318. 318. It went down a little bit. Okay.
You delete one of the zeros.
0.05, 1.05.
Oh, did I get rid of one of the zeros?
No, I'm saying you delete one of the zeros, so I did that.
Okay, let's try 1.1. Okay. It went too high.
1.05.
1.0.
Okay, let's go back up. Yeah, so yeah, we did. We want a lower standard deviation and it dropped now. It's 0.003 or 0.028. Okay, so this is good. Now, you realize how tedious this is, right? And so that's where solver comes in. Now that we have a single number, and this is the key, you have to have a single number called a figure of merit. So write that down, figure of merit. Figure meaning a number, right? A figure of merit. And without a figure of merit, you can't do optimization. So I'll go ahead and write this down. And merit, it's how good something is. This is our figure of how good something is. And it's the standard deviation of our simulated to our experimental. Okay. So we go up to the data tab. A few weeks ago, I said if you don't have a data analysis, then you go through a file. Since we're in a new video, I'm going to go ahead and do that. Options here. You come down to the add-ins. And down at the bottom, you have Excel add-ins. You hit go. And there's a couple of options here. Analysis tool pack, which allows you to do linear regressions. And then solver. You click that solver add-in, hit OK, and then you get these two buttons here. So we click the solver button and we get these options. And so it's an objective cell. Our figure of merit is our objective. We want it to be low. So we want to set that objective to a minimum. Maybe you want to maximize something. Maybe your fit is, high is better. Okay. It depends on your figure of merit. Okay. Ours, we want to minimize the standard deviation. So we're going to set it to minimum. Don't say 0. 1, you're never going to attain 0. And 2, it since you can't attain it, it will say, sorry, we couldn't find a solution. Okay. So, but sometimes you want to aim for 0 and don't want to go negative. Negative is less than 0. And so if you set it to a minimum and it can go negative, sometimes it runs away and it runs to negative numbers. And so you just have to know what your figure of merit is going to do. And in our case, it's a standard deviation. It's going to get lower and lower and closer to 0, but never quite reach 0. So we want it to be a minimum. So this is like a sentence. Set objective D18 to a minimum by changing these variable cells. You see the sentence? So you fill in the different pieces. And so we come up here, D18, we select that, we go in here and click our value. It already was in there because I had already done solver on this spreadsheet. And then changing the values. Okay, let's optimize our baseline first. Okay, just to make sure it's good. So we're going to come up here and we're going to change just the offset and the slope of our baseline. And now let's look at, we're at 0.0028. You want to write that number down so I don't forget it, 0028. And I'm going to hit go. Now we have other options here. We have GRG nonlinear, simplex XP, evolutionary optimization methods. Beats me. Okay. You could Google those and find out what they're telling you. I just use the default. Okay. So this GRG nonlinear, that's fine. Fine for me. Okay. And so it says, we found a solution. All constraints and optimality conditions are satisfied. And it went down slightly, I think. What was our old one? 2.8.
I don't know if it moved.
You don't know if it moved? Okay.
Yeah, I have 285 written down.
Okay, so it didn't really move. Our baseline was already kind of optimized. Do you want me to de-optimize it? And then, well, our peaks, we'll see what happens to our peaks. Now, we can do peak centers independently from peak heights. We could do the width independently and so on. And so let's go ahead and set our objective to a minimum by changing. Let's change our just our peak centers. Let's just do 3 at a time. So we do our peak centers. So we're just going to shift our peaks left and right. Okay, yeah, 0.0023 now. And it adjusted them slightly. Look how many more decimal places we have. Okay. And so then we see that there's still a gap here in the top of this one, and there's a gap in the dips too. So let's adjust our peak heights. And this is the technique that probably yields the best results, doing your optimizations in little groups and then opening it up to full freedom, okay, letting it optimize everything at the end. Okay. So we're just doing the peak heights now. Okay, 0.0017. Okay, that's great. And see, now our peak heights look good. Okay, and still though there's some of these little gaps and so on. Let's let it mess with the width. So let's just do the width by itself just for grins. Okay. It went down a little bit, 4/10,000ths. Okay.
Mine, I have a different figure of merit than what you have.
Yeah, okay, and there's going to be some slop because we're optimizing to a minimum, right? And just like in Gaussian, we have optimization criteria, and yours is going to hit in a different place if we start from a different place. So they hop down this hill, predicting where the next location will be. They take the step, they calculate it, and when you get below these optimization criteria, it stops. Well, if you start a different place, you're going to end at a slightly different place too. You're going to be either deeper or not quite as deep in that well. Now we can adjust those optimization parameters here under options. Constraint precision, we have it set to 1 times 10 to the minus 6. So that's sort of how tight we optimize to. And again, I don't really fiddle with these, but they're there. Okay. Now let's try to break it. Okay. Let's like I said before, if we try to do the baseline without any peaks, let's do that one. Okay. So I'm just going to zero out these heights. Okay. So I just have the baseline. And I'm going to optimize the baseline without any peaks. Remember, we just have a constant and a slope to try to match all of these. Our figure of merit's pretty bad, 0.028, because of this all this area in the middle that's not matching. Okay, so we'll do solver, and we're going to change just these 2 cells. It says it found a solution. Okay, yeah, because it found a minimum. But that doesn't mean it's a good solution. Okay, so we'll hit OK. And look where it put the baseline. Why did it do that?
Because the average is good.
Yeah, the average is good, right? It's the residuals in this area. Again, residuals are simulated minus experiment. So simulated minus experiment, these residuals are positive. And these residuals are all negative. And these residuals are positive. So that means that this found a minimum by drawing the baseline halfway up or a portion of the way up so that the residuals all cancel each other out, and that's a minimum. Okay. The way they're squared, right? But then if I move this up too high, then the negative ones get larger. And if I move this up down, these positive ones get larger. And so that does find a minimum, even though it's squaring the negative ones and making them positive. Okay, so that's why we want to have that's why just a baseline itself is not going to be very useful unless I restrict these residuals just to these regions. So let's just do that. I'm going to come down here just for grins. We're at 29. Let's go to 2950. 2950. So I'm scrolling down here. Here, 2950. And I'm going to take all the residuals from there down and just delete them. Okay. And so I'm only evaluating the overlap on the baseline from 2900 to 2950. But if I can match this, it's probably going to be decent. Does it make sense? I'm picking a baseline region to match for my baseline optimization. So let's go to Solver. And we've got our same figure of merit, our same cells, these baseline cells to match. And now the figure of merit's only responsive to that 2900 to 2950 region. Do you see the tool that I did? I just changed my residuals to pick the places I wanted to optimize. And you could be more complicated than that. You could go down in 3050 to 3100. You could leave those residuals in there too. I was just lazy, right? But you could pick your baseline regions and get a really good baseline.
How did you just tell it which residuals to use?
I just deleted all the others. So I just went down here after 2950 and just selected to the bottom and deleted them. Yeah, I used my hotkeys and just deleted those. Yeah.
Okay.
So that's one way to do the baselining that may be useful for you as you're doing yours. Okay. You can pick the regions between your peaks or above and below your peaks. In fact, I've put in your spreadsheet. I'll show you what I'm talking about. This homework assignments spreadsheet that you guys are going to use. Come on, where is it? Oh, different class. Sorry. Yeah, the homework. Okay, so this is your assignment page. You have the full spectrum here. You have 4 peaks that you've been assigned. Here's your assignment. Here's everybody's assignment, R12 and R11, like we're saying for Murad and so on. And then you're going to do the convolution or deconvolution, and then you're going to put in your data on your centers and intensities on the results spreadsheet that's been shared from Blackboard. Okay, but look what I've added in here. I've added this comparison range. So this is a range which you can use for your residuals. So I've made your residuals an if-then statement. So I'm saying if we're between the range up here, then calculate the residuals. If we're not, don't. Okay, maybe I've made life too easy for you, or maybe I've made life more complicated. I don't know which, but like it's real easy to just delete the residuals you don't want, but then you got to go put them back later when you want them back. And so I went ahead and put this comparison range here and the plot parameters. So there's 3 ranges that you have. You have this, in your case, this x-axis on the plot. So I'm going to double click that and come up here, and I'm just going to go from I don't know, 2900. Whoa. Too many things here. 2900 to 3100. Okay, actually I want to go probably 3080 to 3100. Okay, and my y-axis, I only want to go to 0.2. So I want to get this where I can see my peaks, okay? And so I'm doing Murad's assignment for him here. So here's this on video. Congratulations. Okay. So here's my experimental spectrum. Here's my simulation down here. Okay. I have my baseline. I have peak 1, 2, 3, and 4. But these are the yellow cells are the things that I change, right? And so for my baseline offset, let's do the slope first. It's going to be something like the other one, like 6 times 10 to the minus 6. So 6e minus 6. And there it is. It's showing up at 0.02. Okay.
You're showing about 0.09.
Yeah. So let's go with.
To the minus 5.
We could do that. I'm going to do the offset now. So 0.0. Let's see. 0.08. Nope, too high. 0.07. Okay, that's pretty close. You see that? So my baseline is on there, my peaks are on there, but I want to set my comparison range for the residuals just with this middle region. Okay, so I want to go, what do you say, 3094 down to 3088? So just go 3088, 3094. And so there's my standard deviation for this middle range. And I'm going to use that then to optimize my baseline. So let's go ahead and do a data solver. I'm going to set my objective, which is my standard deviation, to a minimum by changing the baseline cells. So I'm going to change those 2 cells and go. Okay. Whoa, why did it jump to the other spreadsheet?
Because you deleted those.
It didn't change this. That,
Go back to the one and look at solver.
all right, let's do solver again. Maybe it was referring, see, D18, that's correct. We just go ahead and select it. I mean, I see that it's selected, but no. Let's D18 by changing B2 and B3. Can you see anything else weird? No? Okay, go. Wow, why is it going to the other?
Close to this one.
Yeah, I'm going to close this one. Yeah, that's so strange. Okay, I'm going to close that one and we'll just play with this one. Solver, D18, B2, B3, solve. Yeah, that was by far the most bizarre thing I've seen. I'm running solver on one workbook and it jumps to the other. Okay. So we've got a decent baseline. Let's expand this now 3080 and 3100. So we're looking at the standard deviation for the whole spectrum, and then I can move my peaks around too. So let's see, which one is this? 3090. Okay, it's that top one. So let's just do undo on that. And so then I would suggest, you see the procedure here that I've written for you. Zoom in the plot, set the boundaries for the simulation and the comparison regions, manually change the peak locations for all 4 peaks, and increase their intensities, adjust their intensities manually. Use solver to minimize the residuals while changing the baseline parameters. Use solver to minimize the residuals while changing the peak locations. And then let solver change the intensities. So you're doing this piecewise. And if the spectrum and simulation match well, then you're done. If not, repeat 5, 6, and 7. So we're looking at this, you know, this little gap here. Let me just zoom in. It's hard to get rid of. Whoa. See, it doesn't a perfect match there and there, but it's pretty close. The peak center on this one is off. And so I would try to get this peak to go to a higher wave number value. Okay.
So adjust that one individually and then on solver again?
Yeah, and so you might adjust this one a little bit, peak 4. Let's go 3083.5. Let's make it 0.6, okay? See, that was too much. So let's undo. Let's go to 0.55. Yeah, that was too much even. Oh no, it's the black curve is I need to go down a little bit. The orange curve is our experiment. So I need to go down a little bit.
So the orange curve
0.4.
is the actual data.
Yeah, the orange curve is the experimental data. Yeah. So I went down a tenth of a wave number and that looks better. So, you know, I want you to tweak this like that, get it close. Then we come and do solver. If you really want just that one, you can have solver just change that peak and see what you get. We go there. Just that peak center and hit solve. And so, yeah, I dropped it just a hair. Let's see what it did to the spectrum, though. See, I think it changed it too much. And once again, solver is fighting the residuals and that are summed up over all these different places. And so if you want to just compare the residuals in this region, then you can narrow those residuals to be calculated from 3084 to 3082 and just really zone in on that one peak. So let's do that. Okay, and then we'll do solver just on this peak. Yeah, it's still, yeah, I would say that's still off,
Look at the peak's the right shape, it's not the right position.
Yeah. And so this is again, these are the four hardest ones to get the perfect, because if you go to the larger peaks, then any kind of change in peak location creates a huge change in your residuals and a huge change in your standard deviation. Here we're trying to capture that little bitty bump, for that R12 and R11 line. Okay, so have fun fiddling with it. You do your best on all your peaks, and then we'll have, again, our best assignment of this spectrum that's possible, because it will be even between our data points. Notice there is no data point that is that value. So we're getting the peak center that is a higher resolution than our spectrometer can deliver, okay, by using all of the data in the plot. And so that's, I guess, the strength of deconvolution is we're using all of the data points across the whole peak to give us that peak center and the peak height, instead of just the maximum data point on the peak in the experimental spectrum.
Now, would doing some data analysis and smoothing the data, we said we have a lot of noise,
Yeah.
and there's mathematical ways to do that. Would that be a good thing to do? Like if you're doing this for a paper and say, well, I'm going to smooth the data out with this function.
Yes, what you would want to do in smoothing, and that's a whole nother topic, the best method for smoothing data is called Fourier transform smoothing or Fourier smoothing. What you do is you take the peaks and you reverse Fourier transform them. So then you turn them into a frequency diagram. And so then all of the peaks are essentially cosines, and the highest frequency cosines are the ones that are out on the tails of that interferogram. And you can delete those because your noise is high frequency and your signal is low frequency. So your first huge cosines are your low frequency signal, and the high frequency tail of that interferogram is the noise. So you can just zero it out, and you can create a smooth function that takes it to zero, and then you transform it, do a fast Fourier transform back, and you get a smooth spectrum. Now there are spectroscopic packages like thermograms, maybe Igor. There's packages that are made for dealing with spectroscopy, not just Excel. Okay, Excel is just a spreadsheet, and they will have options for Fourier smoothing, and they'll have a percentage of the interferogram that you're deleting. And so I've done Fourier smoothing up to like 60%, 70%. I'm throwing away 70% of the frequencies in my spectrum, but none of those were my signal. They were all high frequency noise. Now you can do this over and over again, and when you see your peaks start to broaden out like they're melting, you've gone too far. Okay, and so you sort of take a before and after picture, and if your peaks haven't changed their height and width, then you're okay at deleting that much data in terms of your Fourier smoothing. You're really just deleting the high frequency noise and then retransforming it. Okay, so that's a bit on Fourier smoothing.
But probably not useful for this assignment.
No, we don't really have a way to do that in Excel. I've done some Fourier transform stuff in Excel, but I haven't I don't have that technique down. So this is spectral deconvolution. You can do it in some of those spectroscopic packages, which again, that may be preferred if you're going to be a spectroscopist and do this over and over again. I mainly teach all of these things in Excel for two reasons. One, you'll always have access to Excel or some kind of spreadsheet. Even Google Sheets will probably do this. Okay, I don't know about Solver, but I think it probably has something, an optimizer of some sort. And two, if you can see it in Excel, you have a better understanding of how it works, right? We have our peak centers here. We generate an individual peak there, and our simulation is just the sum of all of those signals at every wavelength.